We'll get started with chapter number 10, where we extend the idea of hypothesis testing from one sample to two samples. So if you're collecting some data on EVs, how many miles they can go on a single charge, and if company advertises that it's about 300 miles, so you collect sample and it may look like this. So you collect data maybe on 30, 40 or 50 EVs or same EV charging many times, and you get like different mileages depending on like many other factors, obviously, whether you are driving on highway or in city, is it hot, cold, temperature, so all those things affect mileage. But it's a one sample test. Now, there may be times where you are comparing two different companies which claim something similar, and you collect data for those two companies. So this could be based on data from EV1, and this could be EV2. And you want to compare whether they give consistently high miles or not. So the only thing that changes is instead of one sample, we have two samples. So I'm going to compare scores in test 2 and scores in test 3. There are about 30 students in the class. Average based on test 1 was 87.32%, and that improved to 93.22 in the third test. Standard deviation based on these samples was 23.22, 5.52, and sample size, there were 32 here and 31 here. So basically, we want to test our null hypothesis here is mu2 means second test is equal to performance in the third test. Second is not equal to test 3. So after we do all the calculations, ultimately you'll get a p-value, and based on the p-value, either reject HO or fail to reject HO. That's our rejection rule. So there are only two situations possible. If p-value is less than equal to alpha, reject HO. And second one is if p-value is not less than equal to alpha, cannot reject HO. We have data summary. We have the two means. Do you think they are similar or means are very different? So this is a sample. We have 33 students in the class, and 32 took a test number 2, 31 took test 3. So if this test is given to, let's say, in next several semester, I give it to thousands of students. So is it likely that there will always be this kind of difference where test 3 scores are higher versus test 2? Or whatever we see, it is just a random fluctuation. So next class may have totally reverse. So another sample may give us totally different outcome. So maybe this is 90 and that is 87, 88, something like that, because that is quite possible. So do you think it is sampling fluctuation like that? It can change? Or you think that difference that we see, 87 to 93, about 6% difference is there? Do you feel it is large enough to conclude that actually they are different? Another way of asking that question is, do we need any statistical test to prove that 87 is different from 93? 87% is different from 93%? Or you think you can conclude without any further statistical test or analysis of like going through hypothesis testing, doing all the math, and then figuring out? Or can we jump to this conclusion, looking at the two numbers? They seem very different. So what do you feel? Yeah? You feel they are not similar, and what could be the reason? Yeah?
Different.
Why?
Well, the mean on test 3 is much higher, and it's pretty much the same sample size.
So you are saying sample sizes are close, like 31, 32 may not be that big a difference, but difference between means is big. 6% difference you feel is really. There is something called statistical significance. We do all the testing and find p-value, but then there is also something called practical significance. And you see practically that 6% gap, and you feel 6% is too large, that if this process is repeated next semester, the chances that students will perform better in test 2 are less, because the gap is so big. The type of questions that I have, if I give same questions, probably they will again do better in test 3. So that's your thinking. So there could be like some clear-cut thinking that looking at the data, but sometimes also there might be confusion, because how big the difference, it should be like, instead of 6%, if the difference was 5% or 4%, what about 1%, 87 versus 88? Then what would have been our conclusion looking at the numbers? Very difficult to say. So somebody may say 87 and 88, there's no guarantee. Like next time, things can change. But how close is close enough, how far is far enough, could be something that people may judge very differently. So the only way to come to a clear-cut solution or conclusion is go through a scientific process and arrive at the p-value, and then either reject HO or do not reject HO. So let's look at this example. You have data from a company that produces coconut milk. They take coconuts and extract milk inside by drilling a hole and pouring the milk into vat for processing. They have a day shift, and then there's a night shift. They would like to know if day shift and night shift are equally efficient in processing coconuts. So they conduct a study and collect data from 9 night shifts and 16 day shifts, and average number of hours to process 100 pounds of coconuts. So that average was 2, and for this shift it was 3.2 hours. Sample standard deviation based on the samples is also given. Null hypothesis and alternate hypothesis. Null is that mean performance in shift G is equal to mean performance in shift B, and they are not equal for alternate hypothesis. In R, what you will do is you will use the same library that we used last chapter, BSDA. We will use the same function, tsum.test. It's t distribution because standard deviation is calculated from the sample, or sigma not known. And that is most realistic situation. We never know what is the population standard deviation, but we can estimate that using sample. You need mean dot x. So mean for the first population, standard deviation for the first population, sample size for the first population, mean dot y, second population, you need mean, standard deviation, sample size, and you need confidence level. You also need mu So I will let you know what is mu very soon, and whether we are using lower tail, upper tail, or two-sided test. So mean for the first one was 2. We put a comma. Standard deviation 0.866. We put a comma. Sample size was 9. Confidence level 95%. Mu, we have two numbers, UG equals mu B. This is same as you take mu B on the left, it becomes mu G minus mu B equals 0. So mu G minus mu B is not equal to 0. So difference between the two means, if they are same, it will be equal to 0. If they are not same, they are not equal to 0. So that's what we use. That difference we use here to indicate that we are looking to compare the two means and see whether they are same or not. And alternative is two-sided because we are using not equal to. So within quotes we say two-sided. So this is what we'll use to save time. So we go to Posit Cloud and log in. So I'm using business statistics folder. So I'm going to close down everything else. Clean this up, third window. Remove this. So we'll create a new file R, and we'll save that file as chapter 10 so that we can go to files and access that chapter 10 anytime that we need. We'll close chapter 9. So this is going to be chapter 10. I will repeat whatever I wrote there. So library, BSDA, run that. tsum.test, select that, and say mean x is 2, comma, s.x 0.866, comma, enter. Sample size was 9. And then second population mean dot y is 3.2. Variability in the second sample 1. Sample size for the second sample was 16. Confidence level 0.95. Mu 0. Alternative two-sided. So two-sided within quotes. And that gives our output. So this is called Welch modified two-sample t-test. And it summarizes the data for x and y variables. It finds t-value, degrees of freedom, 18.847. Ultimately, you get a p-value based on which we can decide whether they are similar or not, and p-value is quite small. It also gives confidence interval, 95% confidence interval for the difference in means. So you'll find both the numbers are negative. Both the numbers are negative means it is likely significant. If one was positive, one was negative, then it may not have been. So we can write conclusion But before we do that, I will also copy and paste this whole thing so that we don't have to type again, and enter what we had for test 2 and test 3. So it is 7.32 was the percentage in test 2, 23.22, 32 students, 93.22, 5.52 with 31 students. You run that, and the p-value is 0.17. When I asked this question, I think I got 2 replies, but both mentioned that the difference looks quite big, 6% difference between the 2 tests. But it fails. Since p-value is not less than 0.05, there's no difference between the 2 results. So it looks into not only the mean looks very different, but then it also looks into the standard deviation, your sample size, uses proper distribution, and then tries to give some idea about what will happen in the population. If I run this class for next 10 years and I get like 3,000, 4,000 students, so we are thinking of that population, how they will do. So it will happen that in many semesters, students in taking test 2 will score better than test 3. It is very likely because there is no difference. So I will write that down. Since p-value is less than or equal to alpha, p-value is 0.005 and alpha is 0.05. So since 0.005 is less than alpha, we can reject HO. We can reject HO means this is not true. This is true. Performances or productivity in the 2 shifts, night shift versus day shift, are different. This mean of 2 and mean of 3.2, they are able to process like much more in night shift. And once you find that statistically it is proven, or statistically you get a result like that, then you can see why. The reasons become more clear. If you go to any manufacturing plant, in day shifts you'll find all the managers, all the supervisors, everybody is active. And sometimes employees are not able to work freely. But in the night shift, those people are not around to disturb them all the time. So they become more productive in the night shift. So since p-value is not less than or equal to alpha, we cannot reject HO. So we cannot reject. HO means this is true and this is not. Like initially we thought the means that we are looking at seem to be very, very different. But statistically, you find that the p-value is only 17%. What is the meaning of 17%? You subtract that from 100, so 100 minus 17 is roughly 83. So your confidence level is only 83% that they are different. And you want like confidence level to be high, 95%. 83% is considered very low. So what we see with our eyes sometimes may deceive us. Let's do one activity. So we'll use 2 brands of paper clips, one Office Max and other is SBC. So you can treat them as like 2 products coming from 2 different companies, and for some reason you want to test their strength, you will compare strength of two paper clips. So this is a paper clip. And one method, sometimes we have to devise methods to figure out what is the strength. So I want to test this to see over multiple uses, like day in and day out, when it breaks. But doing that can take a lot of time. You bring some papers, use the paper clip, maybe thousands and thousands of times, so it can take forever. So sometimes we have to do accelerated testing. We have to speed up the test by increasing the severity of the conditions. So what we'll do is, you open this to about 90 degrees and count that as 1. Bring it back, count as 2. Open 90 degrees, count as 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Keep on going till it breaks. So about 23, it breaks. So your data point for Office Max number 1 will be 23. And then you take the second sample, repeat this. You may not get the same result. Although they may be coming from same batch or same company, but something may be different. So note down the second number, note down the third number. Repeat with second company, 3 numbers. Find mean for both situations, standard deviation, sample size. So you are testing whether or not strength of two types of paper clips is different using 95% confidence. So your alpha is 5%. Write down your conclusion and also list 5 variables based on what you're thinking that you think may have some impact. Take 1 per team and 3 samples of paper clips. So in the last class, you did a team activity with the paper clip. We compared Office Max and SPC paper clips. So this was one of the data from one of the teams, 27, 26, 29. So with that, we can get mean and standard deviation using mean and SD. And we repeated this for SBC. And the data was 56, 63, 38. And then we put this in tsum. So I'm just changing the means to the new ones. So X 27.3. Standard deviation was 1.527. Sample size 3. 52.3. $12.897. Sample size was 3. So in this case, p-value came to 0.076. So with 95%, we cannot actually reject because p-value is not less than 0.05. So mean look very different, 27 versus 52. but then you still cannot reject null hypothesis because you are also taking into account variability in the data. Since p-value, which is 0.07, is not less than alpha, which for us was 0.05. So 7 is not less than 5, obviously. We cannot reject the null hypothesis. When we conclude for null hypothesis, we say that there is no evidence in the data because everything depends on data. So based on data, we cannot reject the null hypothesis, means they are similar. So the question comes like why the two means are so different, but still we are not able to reject. So you listed some of the reasons like why this strength may vary, apart from just that they are from two different companies. So they may have come through like two different processes, but the reason, the actual strength that you measured varied. One of the reasons somebody gave was speed with which you count the turns. So if you have done like Office Max earlier and you were moving with one speed, and by the time you reach SBC, your speed increased, so that would have added to that confusion. Similarly, angle. It is very difficult to maintain exactly 90 degrees. So if two different people are doing, maybe they are using slightly different angles, that can have an impact. So because of that, when like this kind of testing is done in a company, they take like a lot of pains to make sure that the variables that are difficult to control, like angle for example, so they don't leave it to chance, but maybe create some kind of fixture, and it always goes to only 90 degrees. Otherwise, your comparison will be very confusing because you clearly see 52 is very, very different from 27. But because your variability was so high, you were not able to reject. Your standard deviation was so high, 12.89. So 12.89, that's a big standard deviation. So you have one paper clip that went for 63, another one only 38. So there's no guarantee what next batch will bring. Like you take another 3, you may have like all 3 very low values.